Hello, and thank you for your interest in our research. This presentation will cover exploring electrical charge and solution process composites in order to create new storage materials. Our end goal is to determine a way to create a supercapacitor that can store energy on a grid scale. To introduce the research team, the lead faculty on this research was physics professor Nelson Coates, while the undergraduates in this were Brynn Harrington and Jaku Yeki. Unfortunately, Jaku Yeki has an internship to partake in, so this presentation was created by Professor Coates and Brynn Harrington. To begin, we will discuss the world's current problem of energy storage, along with the possibility of developing supercapacitors for energy storage. Currently, a constant power supply is generated for the grid, which is generally an overestimate of demand to account for possible brownouts. This results in a significant fraction of energy generated being unused and therefore wasted. We will continue into using the physics principles of parallel plate capacitors and the fabrication of solution process nano-composites. We hope to engineer these composites with electrical properties capable of higher energy storage within capacitors. This research will likely be the cornerstone of future capacitors with higher energy and power density capabilities being used for grid-scale energy storage. As this will be mentioned frequently, to define the difference between energy and power density, the simplest way to think of it is energy density is how much total energy a capacitor can store, while power density describes how quickly energy can be put into or taken out of the capacitor. Currently, the greatest problems for energy are pollution and overproduction. In the US, fossil fuels still make up over half of the net energy generation, while renewable generation is under 20%. As you likely know, fossil fuels emit greenhouse gases that lead to rising temperatures on the planet and pollute the air with toxic chemicals. Unfortunately, the heavy use of fossil fuels is due to renewable energy's intermittent nature. Obviously, the sun will not constantly be shining on photovoltaic cells, nor the wind always spinning the turbines, indicating a need to fill in this energy gap. As of right now, fossil fuels are used to fill this energy gap. Although renewables offer a partial answer to reducing pollution, they cannot solely be relied upon to meet grid demands. It is important to note, however, billions of kilowatt hours of energy can easily be produced from renewable sources. But because of the lack of electrical energy storage being deployed in the US, the energy generated by renewables must be used immediately or it will be lost. The US Energy Information Administration, the EIA, offers real-time data of energy generation and demand in the United States. This demonstrates the overproduction of energy, and being from the University of Portland, we will use the Northwest data as an example. As seen in Figure 1A, the US Northwest has a fairly accurate algorithm for estimating the amount of energy consumption, but the model needs to be consistently skewed to overgenerate because of the possible brownouts that can result from an undersupply of electricity. Brownouts can cause significant damage to our household and industrial electrical devices. And so, for example, the generation of energy is approximately 5 to 10,000 megawatts higher this week than it needed to be. Now, looking at Figure 1B, the US Northwest also produces an annual oversupply of electrical energy on the order of hundreds of thousands of megawatt hours. Not only is this a waste of resources that produce unnecessary pollution, but power companies charge their customers for their net power generation, which leads to increased electricity costs for everyone. The ability to store and discharge large amounts of electrical energy at fast timescales is a solution for both allowing a greater deployment of intermittent renewable energy sources and reducing the need for consistent overproduction of energy. Accordingly, the purpose of our research is to demonstrate the potential of nanoscale solution process composites for high energy and high power density electrical storage devices. As companies see this eco-friendly and cost-lowering energy storage opportunity, the development of low-cost supercapacitors as energy storage will likely increase. Even with companies denying the real cost of fossil fuels on the environment, the economic benefit of spending less on electricity is mutually attractive. With greatly improved energy storage and the flexibility in controlling the time of charging and discharging power, capacitors are likely the future of energy storage within electrical grids. Currently, the types of energy storage technology are pumped hydropower and certain batteries, but neither can efficiently be used on an electrical grid scale. Pumped hydropower requires initial electrical power to pump water uphill, and then the water will flow back downhill again to produce energy through generators. In 2019, the US ended up wasting roughly 5 billion kilowatt hours of energy through the system, indicating that the energy conversion processes for the system are not very efficient. As seen in Figure 2, batteries have a high energy density, meaning they can store a lot of electrical energy, but they lack the power density or the ability to distribute energy very quickly to meet grid demands. Whereas capacitors have high power density but low energy density. Neither are currently able to be used on the grid due to these impositions. Our goal is to design a nano-composite that has electrical properties capable of maximizing energy and power density in a capacitor to match the supercapacitor's properties in Figure 2. With the high power densities already achieved with existing capacitor technologies, we will focus on increasing the energy density as a promising solution to a wide range of grid-scale electrical storage challenges. By using parallel plate capacitors, we plan on fabricating a composite to increase overall capacitance to overcome the imposition of the lack of high energy density while maintaining high power density. We hope this encourages the incorporation of this type of storage into the grid and increases usage of intermittent renewable energy and decreases fossil fuel usage. To transition into the physics principles of capacitors, we will look at basic visualizations and mathematical descriptions of capacitors. As seen in Figure 3, a basic interpretation of parallel plate capacitors' capacitance is the measure of the ability to store electrical potential energy. Regarding Figure 4a, the area of the plates and the dielectric constant are proportional to the capacitance, while the distance between the plates is inversely proportional to the capacitance. A dielectric material is typically an insulator between the plates, where in Figure 3 it is a vacuum. Capacitance is measured in farads, hence the F unit following the equation. Conventional capacitors increase their energy storage by using what is called a high K dielectric material in between the electrodes, which polarizes and thus allows for an increase in energy density. But the fabrication constraints of this dielectric layer lead to an increase in the distance between the electrodes, which then decreases the capacitance. Our research explores the idea of engineering capacitors with enormous interfacial area by combining materials in solution, and then, after casting the solution on a substrate, using the difference in entropy of mixing the two materials as the solution dries to induce form a large area nanoscale self-assembled composite. In this composite, the two electrodes are in intimate contact, but with an energetic barrier for charges to pass from one to another, and so the composite can have an enormous interfacial area, separated by a short distance defined by the extent of electronic orbitals of the materials. The enormous capacitance of this geometry can maintain a large power density while significantly increasing its energy density. Again, our goal is for this research on heterostructure composites' electrical properties to provide a foundation for exploring high energy and high power density capacitors. From Figures 4a and 4b, it is easy to see that capacitance is only dependent on the geometry of the parallel plates and the dielectric material between them, since the current and/or voltage being sourced will be known. Single material charge transport systems within capacitors are common in the past, but there is a large transition to engineering heterostructure composites to surpass the limits of single material composites, which will be discussed further in the literature review. This basic idea of how heterostructure composites can benefit capacitors is shown in Figure 5, which displays an image of the cross-section of the polymer composite fullerene bulk heterojunction taken using false color tunneling by a specialized transmission electron microscope (TEM) equipment. with the heterojunction being between the small molecule PCBM and the solution of P.PSS. Although P. and PSS are a combined solution, for our purposes we are treating it as one material made of strings of polymers, whereas PCBM is a molecule that tends to crystallize. The difference in structure between the polymer P.PSS and the small molecule PCBM is what leads to the significant difference in entropy of mixing that allows for the formation of nanoscale phase-separated composite. Unfortunately, these images often take years of training and are extremely difficult to produce, so we are unable to frequently reproduce similar images of our specific composites. Although the results in this image are essential to defining our research, in this image the red primarily represents an electron conductor while the blue represents the hole conductor. By amplifying this image further, it demonstrates this composite's ideal geometry for capacitance with an extremely small separation distance of electrodes and an extremely large area of the phases PCBM and P.PSS. By equation 4a, this shows the impressive capacitance that could result due to this ideal geometry of minimal electrode separation distance and maximized contact area of the two phases. Although each material will have their dielectric constants upon crystallization, the magnitude of capacitance increase will greatly outweigh the significance of the dielectric product. Using this proof of principle technique, the ability to maximize capacitance by using the equations and characteristics of capacitors was used to rethink energy storage. Our goal is to create a parallel plate capacitor that could be implemented into something like a photovoltaic solar cell, a material that could increase the amount of energy storage while maintaining the high power density of capacitors. By maximizing the contact area between the phases with the newly created composites and decreasing the separation distance, the energy density can be optimized. Engineering the material to optimize this energy density is a significant opportunity to change how capacitors are currently used and adapt them for grid-scale electrical energy usage and storage. Moving into the literature review, we will inform you of the recent research that has inspired this project, including engineering charge transport and the capacitance of P.PSS. As mentioned before, single material charge transport systems are common in the past, but recently there has been a large transition to engineering heterostructured solution process semiconductors, like the composites we are creating, to surpass the limits of the past. The molecules in Figure 6 demonstrate what we plan on using. First, P.PSS, a solution composed of chain polymers, and second, PCBM, a small molecule with a tendency to crystallize. The three largest benefits within the manipulation of the charge transport system include the balance of charges, promoting radiative recombination, and increasing semiconductor usage while lowering production cost. First, regarding balance, the excitons and free charges balance each other much better, so electron extraction for electrical energy is optimized. In regards to radiative recombination, the synthesizing of materials results in spatial confinement of electrons and holes, which increases the efficiency of light-emitting diodes, creating the finite resistance of the capacitor. Concerning improved material and lowering costs, by using solution process semiconductors, the options are no longer limited to firm materials such as metals. The need for mining these materials would decrease, as the solution process composites would be easier to mass manufacture, cheaper to produce. It would no longer be restricted to firm materials. For example, if you think of how firm and stiff solar panels currently are compared to the flexibility of silicon, that's similar to what we are creating. Moving more specifically into P.PSS, the crystallized form of P.PSS, the chemical structure pictured in Figure 7, is considered an electroactive conductor, although its properties have generally been poorly understood. One of our goals is to determine how P.PSS reacts with charges and therefore maximizes capacitance and energy storage through determining electrical properties. P. and PSS have different thermal or kinetic energy responses to electric fields, where P. has more thermal energy, meaning even if both are at the same temperature, P. will have more energy than PSS. Additionally, the composite has a breakdown at 150 millivolts, so the composite's capacitance is optimized below this breakdown level. Under recent two-dimensional evaluation, the different amounts of energy between p-dot and PSS cause electrons to move to lower energy areas where electrons diffuse into the lower energy material. Given p-dot has more thermal energy, electrons first diffuse into PSS, as seen in Figure 7, creating a diffusion current moving in the opposite direction as the circuit's current, creating a net current of 0. Yet PSS will eventually have more energy and the reverse process will occur, and with electrons diffusing into p-dot, a current will be created in the same direction, allowing charge to pass. The best analogy for capacitors composed of this material is having something like a leaky capacitor, due to some charge being able to pass through. In contrast, ideal capacitors have infinite resistance, where no charge can pass through while the capacitor is being charged. When fully charged, it would act as an open circuit. Rather than offering an infinite resistance, both resistance and capacitance values can be measured at a given frequency for circuit analysis. In conclusion, if using a thin enough composite to resemble a plane, as we are, the structure of electrical layers between the p-dot PSS is the major component of the material's capacitance ability, which rejects the original categorization of it being an electroactive conductor, but rather having electroactive layers, along with hole transport layers and interconnectors. Due to this, multiple capacitance values can be the result between different p-dot PSS and p-dot PCBM values. Within these materials, there are dense holes, allowing for ions to move in and out with its electroactive layers, allowing for varying size and shape under the force of an electric field. By engineering composites of this material, the density of these holes can be manipulated by the electroactive polymers within the electric field produced to increase overall energy storage. Using this material in capacitors will theoretically increase the storage of charge and better the transport of charge within not only supercapacitors, but displays, transistors, and energy converters, indicating this research's application to a multitude of electronic devices. Using the ideas introduced, the next step was setting up for fabricating and the testing of the heterostructured composites made of a variety of crystallites with different volume ratios of p-dot PSS. We asked questions to set goals for our research and began the setup and experimentation process with a gold film, until the unfortunate imposition of the coronavirus. To reiterate our research plan and goals, here are some of the questions we are trying to answer through experimentation of different electronic composites to increase energy storage in supercapacitors. Firstly, what volume ratio of the p-dot PSS composite will maximize the surface area of the capacitor? Will the intermediate composite and equal volume ratio of p-dot PSS result in the maximum area? Secondly, is the capacitance we measure significantly larger than what we would expect from a fully mixed composite, i.e., does the large interfacial area resulting from nanoscale phase separation increase the capacitance? Lastly, using this composite, will the output of power and energy density be high enough to offer a promising possibility for grid-scale storage, i.e., can similar composites be engineered for grid-scale energy storage? With these questions in mind, to begin our research, we reviewed research techniques, including the Vanderpot and 4-point probe method, and began ordering materials. The major background concepts for this experiment were capacitance, which we have already covered, the 4-point probe method, and the Vanderpot method. This gave us background necessary to understand the process of alternating sourcing a current and measuring a voltage to determine the sheet resistance of a material. By confirming the accuracy of the sheet resistance through these methods, this will ensure that current and voltage are being sourced and measured correctly from the source meter so other electrical properties can be accurately determined. To further our understanding, Professor Coates provided us with readings such as those in the literature review and about the Vanderpot and 4-point probe methods. This created a solid background for us to understand what we were testing and why this was so important to the future of energy storage. In Figure 8a, this is a display of setups for probe placements within the Vanderpot method. Different geometries resulted in more accurate results. We used Part B of the geometries, given Part A was a difficult geometry to produce for a nanoscale composite. Lastly, being Professor Coates' first year at the university, ordering necessary supplies was required to complete this research. This required looking at past purchase details and determining the kind of material or devices we needed to pursue the research. Using the van der Pol method just discussed, our first application of our platform was to measure the electrical conductivity of nanoscale thin films. As mentioned before, taking images of the cross-sections of the composites requires years of training and access to specialized transmission electron microscope (TEM) equipment. So we assume that varying the volume ratio of the solution is correlated to changing the surface area. From the inspiration of the 4-point probe and van der Pol method, an example of calculations for this research can be seen in Figure 8b, which can take nanoscale films and measure their electrical properties, such as sheet resistance and electrical conductivity as a function of the applied electric field, and the impedance as a function of moderate frequency, with accurate results. However, it is important to note, unlike the literature review, we are not proving the validity of the van der Pol method, as it is already a well-accepted method to measure sheet resistance. Given sheet resistance, which is inversely related to conductivity, we can determine the electrical transport properties of composites with a variety of volume ratios and applied bias. Since this capacitor is something like a leaky capacitor, or a capacitor with finite resistance, the resistance needs to be included in our determination of electrical properties and calculations of capacitance. With this, we can calculate the magnitude of energy and power density. Through these methods, nanoscale composites can be fabricated at low cost, and sheet resistance can be accurately measured by alternating sourcing a current and measuring a voltage on the composite. Additionally, by using nanoscale composites, we can diminish waste from the experiment, contributing to more environmentally friendly research, which aligns with the overall goals of the project. Lastly, the basis of the 4-point probe method, which implicates van der Pol's analysis to determine sheet resistance, includes 1. Determine the van der Pol geometry to use. As stated before, from Figure 8a, we chose Part B of that, which has a square formation with probes on each corner. Step 2. Alternate sourcing a current and measuring a voltage across adjacent corners of a square. And Step 3. Calculate vertical and horizontal resistances separately, and sheet resistance determined on the van der Pol equations from these resistances. With the supplies beginning to arrive, we began to organize and update past computer programs that would utilize the 4-point probe and van der Pol methods to measure the electrical properties of composites. Our next step was to measure the electrical resistivity of a 100 nanometer gold film. We first needed to ensure the accuracy of the Keithley 2400, the source meter pictured in Figure 10 on the left, which is the device that sourced the current and measured the voltage. We used a gold 100 nanometer film with a quartz sticking layer, since the sheet resistance of gold is well known. This was used as a validation of accuracy and precision of our testing platform. Utilizing the van der Pol equations from Figure 8b, we determined the sheet resistance based on alternating the current and voltage sourced and measured. This resulted in us alternating the corners of the film that were sourcing a current, measuring a voltage, and then averaging each resistance value. To better explain how to use the 4-point probe and van der Pol method, the next few slides show how we calculated the percent error of sheet resistance of our gold film to a theoretical gold film. As seen in Figure 11a, we first measured the voltages resulting from a 10 milliamp current using the 4-point probe method. Then, in Figure 11b, we calculated resistance by approximating the relationship between voltage and current as linear, and used Ohm's law manipulation, resistance equals voltage over current. We then averaged them in Figure 11c and used van der Pol's sheet resistance equation to calculate sheet resistance. As you can see, van der Pol's equations are very mathematically complex, but he also had a simplification of this equation, which results in an accurate approximation, which is how we determine the sheet resistance of the gold film in Figure 11d. Lastly, in Figure 11e, we knew that the product of resistivity, sheet resistance, and the thickness of the sheet is equal to 1. With the known conductivity of gold, which is the inverse of resistivity, we calculated sheet resistance to determine the thickness of the film. We determined the experimental value was 101.7 nanometers thick. With a theoretical value of 100 nanometers, the calculated percent error was 1.7%. The results proved that with this incredibly small percent error, that the machine was in fact functioning properly. Figure 11F shows all of the calculations together. Since manually switching the probes opens a lot of possibility for human error, this was an extremely small and reassuring percent error. It assured both the accuracy of the Keithley 2400 and the van der Pol equations. With the accuracy of these manual measurements, the next step was to calibrate the machine so it could work remotely and communicate measurements to the computer to be recorded. The goal of implementing the program was to decrease error further and decrease time spent on measurements to leave more time for fabricating composites to be tested. Unfortunately, we will not have the opportunity to test composites until later this year, but this ensured a properly functioning machine, which was expected as it had been serviced before the experiment. Unfortunately, with the growing concern for safety revolving around the coronavirus, the University of Portland transitioned into online classes. We as a research team greatly appreciate the university's concern for both the faculty's and the students' safety regarding the virus, but this did make our hands-on research come to a pause. Rather than stopping, we decided to evaluate past data to continue analyzing the effects of electronic heterostructure composites and the possible future implications of these composites in energy storage. This allowed us to continue exploring the data and possibly inspire us for future research. To best use the time and the rest of the semester, we used Professor Coates' past research data to determine which volume ratio of P.PSS produced the highest area when synthesized with PCBM, given the electrodes have the ability to touch. The main focus was on finding computational methods to evaluate the composite data. Without being able to physically meet, we were able to video chat through Microsoft Teams and largely focus on the implementations of the components measured to extract capacitance. Within the past data, there were 3 composites with different volume ratios of P. to PSS, but we still predict that the 1:1 volume ratio of P. to PSS, when synthesized with PCBM, will produce the maximum area. Without access to TEM equipment, we are using the assumption that manipulating the volume ratio of P. to PSS will result in a change in area. Eventually, we will determine whether there is a change if volume ratios are manipulated, but as of right now, that is our assumption. To begin, we reviewed their process of fabricating the composites. They first used P. and PSS solutions with a variety of volume ratios as one of the phases. To reiterate, for our purposes, although a chemical compound of polymers, we consider P. PSS as a single material. Then they crystallized that solution with PCBM, the second phase. As P. PSS is a long string of polymer chains, these chains are reluctant to change structure, forming the bulk heterojunction between P. PSS and PCBM that generate a large area with minimized distance. The bulk heterojunction creates an energetic barrier for charge transport across the interface of the two materials. Due to the complex structure of P. PSS and PCBM crystallites, impedance can be modeled as some combination of parallel and series charge transport. We then evaluated the composite with the 1:1 volume ratio of P. PSS, also known as A plus PSS, for their experiment. To introduce the data, there were 6 trials at different source voltages, and with the sinusoidal nature of capacitors and alternating current, the resistance, impedance, frequency, and current were measured. The setup of the experiment had nothing outside of the composite affecting charge other than the minuscule resistance of the probes, which can be approximated as 0 for this experiment. So the results are entirely dependent on how the nano-composite interacted with charge. In this data, impedance was calculated using Ohm's law. They used the quotient of peak voltage and current to determine the magnitude of impedance. Since peak current leads peak voltage by 90 degrees for capacitors, the phase shift was also recorded. For analysis, we looked at the graph of impedance as a function of frequency for the A plus PSS data in figure 12a. Given that impedance does have a dependency on frequency, it is important to note that lower frequencies generally result in higher impedance for capacitors. Additionally, capacitance tends to be higher at lower impedance and therefore higher frequency. This data follows that pattern, where low frequency does indicate high impedance. From the general property for capacitors, we assume that due to this trend, this composite is acting as a capacitor. The exact circuit model that corresponds to the complex network of parallel and series electrodes in our composite has yet to be carefully analyzed. But we did notice the following trends in this data: that the impedance appears to be independent of applied voltage at high frequencies, which suggests a parallel resistor-capacitor circuit network, and the low frequency impedance is higher at low applied voltages, which may be correlated with the energetic barrier between the materials of our composite. Although we cannot actually conclude anything from this data, these do pose questions that we can test later and then draw conclusions about the electrical properties of P.PSS for capacitors. Looking at the graph of regular capacitors in Figure 12b, it is important to note that the magnitude of impedance is drawn on a logarithmic scale, whereas 12a is drawn linearly. The impedance versus frequency in 12b demonstrates what we would expect of a regular capacitor in a series RC circuit, whereas in Figure 12a, the different voltages converge to a lower impedance at higher frequencies. Since there is some noise in 12a, much more data will be needed to be taken to truly compare it to a general series RC impedance versus frequency graph. From analyzing past data, the question we are now trying to answer this summer is, are many magnitudes of change of capacitance observed from these composites? Since there is a finite resistance in this composite, we can use the measured resistance to determine the strength of the energetic barrier within the capacitor. The magnitudes of impedance as a function of frequency, or the real impedance versus imaginary impedance, can be applied to a circuit model to extract the capacitance of the composite. Since there is a finite resistance in this composite, we can use the measured resistance to determine the strength of the energetic barrier within the capacitor. The magnitudes of impedance as a function of frequency, or the real impedance versus imaginary impedance, can be applied to a circuit model to extract the capacitance of the composite. Recent studies have shown current density versus voltage can also be used to determine capacitance, allowing us to compare results from the two computational methods. Additionally, single material dielectric properties have been studied for years, allowing us to compare heterostructured composites' energy and power density to them. From this, we can determine whether heterostructured composites' electrical properties can offer a solution for supercapacitors as energy storage. After completing this experimentation, we hope others are inspired to continue the experiment by engineering composites with high voltage breakdowns to be used on a grid scale. Funding for this research is provided by the Provost Initiative for Undergraduate Research and the College of Arts and Sciences, and we thank them both for their support in our project. Thank you for listening. We appreciate your time, and if you have any questions, feel free to either email Professor Nelson Coates at coates@up.edu or Brynn Harrington at harrington23@up.edu. And last but not least, we are additionally grateful for the sources that have inspired and supported this research. Thank you.